All right, so here we go. Let's get started. So what we're going to be looking at is the behavior of the function as we let x approach either positive infinity or negative infinity. So in pre-calculus, you called this the end behavior of the function. And you actually learned some tricks for rational functions to figure out if there were like vertical asymptotes. So one of the tricks is if it's a rational function and the top and bottom are the same degree, then you can just divide the coefficients and that will be what the horizontal asymptote is. But you weren't really told why, and calculus kind of explains why that is the case. So what I want you to do is get your calculator, go ahead and plug that function into y1. And we're going to make a table where we just make x infinitely large positive. I'm going to try and connect my real calculator to my computer calculator real quick. Come on. There it goes. Okay. We're going to go into y1. We're going to do open parentheses, x squared minus 1, divided by open parentheses, x squared plus 1. We're going to go to our table. I'm just going to delete out anything in there. And so now what I really want to see is what's going on when x is getting really, really big, and do my y values seem to stabilize or not? And so you can just start entering big numbers. 10, that's not very big. 100, 1,000, another bigger number. And so you can see what do your y values seem to get closer and closer to as we let x just get indefinitely large. So we say approach infinity. You can't really approach infinity. It's just getting larger and larger. So in the chat, what do our y values seem to get closer and closer to? Thank you. And that's pretty consistent. You can enter as large a number as you want, and if you get big enough, your calculator just can't even take the decimal out that far. It's true, your y values approach 1. Then we want to do the same thing to negative infinity, so going on the left side of the graph. Negative 1, oh, uh-oh. So negative 1, negative 10, come on. Negative 10, negative 100, negative 1,000. And we do see that same behavior from the left and the right. So the notation we're going to use there, in this case, is going to be that the limit as x approaches positive infinity of my function equals 1. And the limit as x approaches negative infinity for my function also equals 1. And the idea is that when we say the limit as x approaches infinity of f of x equals L, it just means that the values of your function can be made arbitrarily close to L by requiring x to be sufficiently large. All right? And so that means that you can give me any value. You can say I want your y values to be within 0.01 of L. And I just have to tell you, oh, you just have to go out this far on the x-axis, and after that my y values are always within 0.01 of L or closer. And so horizontal asymptotes are different than vertical asymptotes, right? Your your function doesn't cross a vertical asymptote, but you can have functions that cross horizontal asymptotes and still satisfy this limit definition at infinity. So you can see this last one over here. This is called a dampening function. There are lots of dampening functions involved with acoustics because sound travels as a wave and it dissipates over distance. So the amplitude of the sound gets smaller and smaller the further it travels, right? Y equals L is still the limit as x approaches infinity, even though the graph is going to cross it there infinitely many times. But it's still getting infinitely close to L. It's just oscillating closer and closer. Okay? So what we'll find out is y equals L is still considered a horizontal asymptote of the function. And like our first slide, this is actually a special kind of function that mimics the membrane of a drum when you beat it, or you can think of like dropping a rock in a pond, and this is like a two-dimensional trajectory graph of the waves. This is a dampening function where y equals 0 in both directions is a horizontal asymptote because the graph just gets closer and closer to 0. Yeah, exactly. As long as the distance, as long as we are getting closer and closer as x is increasing, Audrey, yes, then it's an asymptote. It's a horizontal asymptote. So that's just how horizontal asymptotes differ, right? Your graph can cross them. In fact, it can cross them infinitely, but as long as your x gets larger and larger, your y values get closer and closer to a certain y value, it would still be considered a horizontal asymptote. So let's just give that. Oh, here's your definition from the left. It's the same as the definition from the right, except note that we are approaching negative infinity. Same rules apply. All right, give me a green check when you're ready to move on, please. All right, let's do it. So now we have this definition of what a horizontal asymptote is. When the infinite limit exists, you have a horizontal asymptote at y equals L. So in either case, if the limit of f of x as x approaches positive infinity is L, or as x approaches negative infinity is L, we would say in both cases y equals L is a horizontal asymptote of the curve. Remember that if you are asked for horizontal asymptotes, like if you are analyzing a graph that's given to you and you're asked where are the asymptotes? Asymptotes are equations. So saying 5 doesn't make any sense. That's just an abstract number. Saying y equals 5, that's an equation of a line, which is an asymptote. Specifically a horizontal asymptote. X equals 5 is the equation of possibly a vertical asymptote. All right, give me a green check when I'm okay to go. I have you all completely minimized right now because I'm trying not to record anybody's, faces so I can post this. And this is especially unnerving to me, more so than normal, because at least I can see some of you normally on the computer and trick myself into thinking that I'm having a conversation with somebody. All right, thank you. Find the infinite limits, limits at infinity, and asymptotes for the function shown in the figure 5. Okay. So all of this sounds like word salad. But what we need to do is understand the difference between these. Infinite limits are when our actual limits come out to something infinite. Okay? So this is where we're approaching a finite value, but our y values go off to infinity or negative infinity. So this is where our vertical asymptotes occur, namely. So for example, here, that's -1. We can definitely say, so this is going to be our infinite limits. The limit as x approaches -1 of this function is positive infinity. And I can say the overall limit because on both sides the y values are going up towards positive infinity. Now I have a couple other infinite limits, but they're one-sided, right? So this one at 2, as I approach from the left only, so the limit as x approaches 2 from the left is negative infinity. But on the right, the limit as x approaches 2 from the right is positive infinity. And the overall limit wouldn't exist there because they're doing opposite things. But those are all my infinite limits. And so then from that, my takeaway is that I have vertical asymptotes in two places. I have a vertical asymptote at x equals -1, and I have a vertical asymptote at x equals +2. Right? Questions? All right. Now our limits at infinity, that's our end behavior. That's what's going on as we go way out towards the right and way out towards the left. And so in a problem like this, you would assume that the behavior is consistent outside of what you can see in the graph. So I'll assume as I let x go out to positive infinity, it will continue to approach whatever that value is, which looks like 4, right? So I would say the limit as x approaches positive infinity of f of x seems to be approaching 4. And then on the left, what's going on as we approach negative infinity? Seem to be approaching 2. So there you go. There's my limits at infinity. And from those, we can infer our horizontal asymptotes. And those are going to be y equals 4 and y equals 2. If you have questions, go ahead and type in the chat or unmute. If you're good with that one, give me a green check. Okay. I think we're mostly good to go. Again, if you need to catch up, right now I'm recording it. My computer's not exploding, so I should be able to post this at the end of class. All right, let's talk about how to deal with these analytically, meaning how do we use algebra rather than just the table in our calculator to do this? We're going to use a concept based off of this one example, actually. I want you to conceptually think about what happens for a function like this as you let x get infinitely large. What is going on with the overall fraction? So I'll start with just like plugging in different values of x. So I'll plug in 2, not very big. 10, 100, 1,000, 10,000. What are these fractions getting closer and closer to as I let x increase? In the chat, what are these fractions getting close? Good. They're just getting closer to 0, right? Now, the other thing I want you to think about, does the numerator matter? What if instead I asked you what the limit as x approaches infinity of, let's use a big number in the numerator, 9,999 over x. Now, for a while, you could plug in values for x where you'd get values that are much bigger than 1. But eventually, since what we really only care about is what goes on when we plug in enormous values for x, what is the overall fraction going to begin to approach eventually when I start having large enough values in the denominator? In the chat again. Yeah, still 0. So it might take a little longer, but it doesn't matter because we're going out to infinity. So in the long run, the denominator is just going to eat up that numerator, right? And the whole thing is going to approach 0. So as long as you have a constant in the numerator and your denominator is getting infinitely large, the overall fraction will approach 0. All right? So for the first one, this is 0. Well, what about if I approach negative infinity? So if I use negative values of x, I would have like negative 1/2, negative 1/10, negative 1/100th, or 1/1000th, etc. What are my fractions getting closer to? That's an O, Ian. I'm not counting it. Still 0. It's just they're getting closer to 0 from the other side of 0. They're approaching it from the negative side of 0, right? And you can see that reflected in the graph. As we approach infinity on the positive side of x, my y values approach 0 from the top. But from the negative side of x, my y values approach 0 from the bottom. But they're still 0. And so we're really going to use that. It's just a capital O, Ian. We're going to use that fact to be able to kind of algebraically manipulate some of these. All right, and so we have this theorem. If r is a rational number, then the limit of 1 over x to the r is 0. As x approaches infinity, or as x approaches negative infinity. It doesn't matter. But rather than memorize the technicalities of this, I want you to keep the idea. If your denominator is getting infinitely large and your numerator is a constant, the denominator will eat up that numerator and the overall fraction will eventually approach 0. All right, give me a green check when you're good to go, and we'll move on to what I would consider the most important examples. So we're going to learn how to manipulate these algebraically. All this is saying is if you have a fraction where the denominator is growing infinitely large, so it doesn't just have to be x, it could be like 1 over x squared. If I'm letting x go to infinity, the denominator is still getting infinitely large in this case. It's just getting large faster than if it was 1 over x, right? This is still going to approach 0. Or if you had 1 over x to the 1/2, same idea. the denominator is still getting large, maybe a little slower, but it's still just going to get infinitely large and your fractions are going to approach 0. Yeah. So just keep that big picture in mind. We're trying to discern the numerator is a constant and the denominator is just getting bigger and bigger. The whole thing goes to 0. All right, so let's use that to evaluate this. And this is probably the most important example because I'm going to kind of give you the steps. So if you have a rational situation, what I want you to do is find the highest power of x in the denominator. You're then going to divide both numerator and denominator by that power of x. The idea here is just like we're allowed to multiply the numerator and denominator by the same thing without changing it, you can also divide both the numerator and the denominator by the same thing because then we're effectively just dividing by 1, right? And we're not changing it. You're then going to simplify as much as you can. Then evaluate the limit of each term separately, which our limit laws allow us to do. All right, so for this one, the highest power of x in the denominator is x squared. So I'm going to take my numerator and my denominator, and they're getting both divided by x squared. So you're effectively going to distribute that division. So every term is going to get divided by x squared. So I'm going to have 3x squared over x squared minus x over x squared minus 2 over x squared over 5x squared over x squared plus 4x over x squared. Nope, sorry, minus 4x over x squared. Nope, plus 4x. Plus 1 over x squared. Okay? So simplify. Limit as x approaches infinity. Let's see, 3x squared over x squared just simplifies to 3. X over x squared will simplify to 1 over x. And there's no way to simplify 2 over x squared. That's just going to stay as is. 5x squared over x squared simplifies to 5 plus 4 over x plus 1 over x squared. Now our limit laws effectively allow us to look at each term separately and evaluate them on their own. So as x approaches infinity. So I'm going to have you guys do that with me. Nope, sorry. All right, so the first term we have the limit of 3 as x approaches infinity. The limit of a constant is a constant. So what's that limit going to be in the chat? Yeah, just 3. The limit of the constant is that constant. It's just 3. So that remains 3. Minus, now I'm looking at the limit of 1 over x as x approaches infinity. So what's going on with 1 over x as we let x get infinitely large? What's that fraction going to approach? That's right. Good job, Emily. Good job, Maisie. Yep. That's what we were just talking about. That's approaching 0. Whoops. Okay, what about the 2 over x squared? What's 2 over x squared going to approach as we let x get infinitely large? So we have a constant in the numerator. We have our denominator just getting larger and larger. What's the overall fraction going to approach? Yep. Still 0. Good. And that's what that last theorem said to us. So my numerator is just 3 minus 0 minus 0. My denominator, again, limit of a constant is the constant, so that's going to be 5. As x approaches infinity, 4 over x will approach 0. 1 over x squared will likewise approach 0. And this comes out to 3/5. So this is from where that pre-calculus rule comes from. That's like, if you want to know where their horizontal asymptotes are, and they are polynomials of the same degree in the numerator and denominator, you can just divide the leading coefficients. All right, give me a green check if you understand and you're good to go on that one. Excellent. Let's move forward. All right, so find the horizontal and vertical asymptotes of the graph of this function. So this one's equally as important. Now we're going to use those steps that we learned, but there's a little more trickery here. Let's go back to find horizontal and vertical asymptotes. Well, vertical asymptotes, let's do that first. So for vertical asymptotes, we just look at the denominator. We're going to set that equal to 0. We're going to solve for x. Oh, sorry, I'll go back. Audrey? Yes, 3/5 would be a horizontal asymptote. That's just not what they didn't specifically ask us to find the asymptotes. Otherwise, I would have written it as y equals 3/5. Again, an asymptote is the equation of a line. This one, they just asked us to evaluate this limit. So this limit just comes out to 3/5. But yes, it is also true that because of that, there is a horizontal asymptote at y equals 3/5. Just the wording of the question, all they asked us to do was evaluate, which is why it was okay to just leave it as a number. You got it. All right, so this one, I set my denominator equal to 0. I solved. You also need to make sure that there's not a common factor in the numerator. There isn't, though, because everything's under the square root in the numerator. If there were a common factor in the numerator, then that would be a whole, not a vertical asymptote. But in this case, we do have a vertical asymptote at x equals 5/3. All right, now to get to our horizontal asymptotes, we need to look at two things. What's going on as x approaches positive infinity, and then what's going on as x approaches negative infinity, because you could, and for this one you do have a situation where you actually get different horizontal asymptotes in different directions. All right, so here's what we want to do. What is the highest power of x in the denominator? So the highest power of x in the denominator for us here is just 1. So we would want to divide the numerator and the denominator by x. For the denominator, that's not a big issue. Just divide in the x. We would get 3x over x minus 5 over x. For the numerator, that is a big issue. I cannot just divide in an x that's not under a square root to become underneath the square root. It needs to be under its own square root. So I can do a little algebraic trickery. I can recognize that x equals the square root of x squared, right? So in the numerator, so that I can sneak this x into my square root, I'm going to actually be dividing by the square root of x squared, which is technically still x. But that means that what both of these terms get divided by under that square root is actually x squared. So now this is going to be the square root of 2x squared over x squared plus 1 over x squared. All right, go. No, just the largest. What I wrote down is you just want to divide by the highest power of x in the denominator. Yeah, and since the highest power we have in this denominator is x, that's what we go with. All right, so now I'm at the simplify stage. And we have root 2 plus 1 over x squared over 3 minus 5 over x. And now our limit laws from the very beginning, or towards the beginning of this unit, allow us to basically take the limit of every term separately. We're even allowed to sneak the limit under the square root. So you're just looking at each term separately. What's going on as we let the constant 2 approach infinity? It just stays 2. What about 1 over x squared? What is that going to approach? Yep. 0. Good. Then in the denominator, 3 just stays as 3. 5 over x, again, approaches 0. And I have an answer of root 2 over 3. But they ask us for a horizontal asymptote, so I want to make a note. Remember, horizontal asymptotes have equations. So it's y equals root 2 over 3. Now, everything about this, when we approach negative infinity, is going to be the same. And it's going to come out the same way, except one thing that we have to be careful about. When you let x approach negative infinity, you are using larger and larger negative numbers. What do you know about the sign of the denominator? If I use larger and larger negative numbers, what will the sign of the denominator be? Negative or positive? it has to be negative, right? So if we're plugging in just bigger negative values of x, since we'll have 3 times a big negative number and subtract 5, it's just going to continue to be negative. What about the sign of the numerator as I approach larger and larger negative values of x? Will the numerator be negative and or positive? The numerator is going to be positive because remember, we're going to plug in a negative value for x, but then we're going to square it, making it positive. Multiply by 2, add 1, it's still positive. Take the positive square root, it's still positive. So with larger and larger positive values of x, my numerator is always positive, my denominator is always negative. Well, what do you know? What's a positive number divided by a negative number? What's the overall sign of the fraction going to be? The overall sign of the fraction has to be negative, has to be less than 0, because you're always going to have a positive divided by a negative. But it's the exact same process otherwise. So it has to approach, in this case, the exact same value, except negative. So what I'm saying is that y equals negative root 2 over 3 is also an asymptote here. And that's because the only difference is that my denominator would always be negative and my numerator would always be positive. The only thing that's actually making that occur is this square root with x squared under it, right? If both terms in the numerator and denominator were either x squared, like the last example, in this last example, if we approached negative infinity, we would get the exact same 3/5 because the behavior is the same. We're squaring x, and in the long run, squaring x, whether x is negative or positive, is going to make your output positive. But here, our numerator and denominator are forced to have opposite signs when our input is negative. So if we take a look at that graph, let's just verify what's going on. All right, so we got that vertical asymptote that's at 5/3. And as we go out towards positive infinity, our y values seem to approach something that's pretty small but positive. That's going to be our positive root 2 over 3. But over here, you can see that it does stay negative. That's going to be our negative root 2 over 3. Oh, sorry. Sorry, it's coming up in the recording, but I realize I have to change the share screen. Sorry, so here it is. So we have that vertical asymptote at 5/3, at x equals 5/3. And our limit as x approaches infinity to the right, you can see it's approaching something that's kind of small towards 0, but it just stays positive. So that's the positive root 2 over 3. But on the opposite side, it stays negative. So that's the y equals negative root 2 over 3. And then on these infinite limits, a great tool is always your calculator. You can always kind of use that to justify your answer. If you're unsure, just throw the function in a table and start plugging in large positive numbers and then start plugging in large negative numbers. Because if you're unsure if they should be opposite signs or the same sign, that'll kind of help you verify that, okay? All right. So here's the deal. I don't think we're going to get to 116 today, so I will just eliminate those from the exam, I think. And we'll dump it into section 2. I'm not going to go over all of these, but I'll go over a few. This one in particular is a good one to talk about. So here we don't have a fraction, but we can force it to be a fraction using a tool that we've been using quite a bit, and that's the conjugate pairs. So remember, the conjugate pairs are the a plus b times a minus b is a squared minus b squared. Bonnie, I just saw your question. I will. And the idea for something like this is, let's think about what's going on just for this term as x gets infinitely large. Well, it's a square root function, so it's still just getting infinitely large. It's just doing so at kind of a slow pace. But your y values, your outputs will still just approach infinity. Well, what's x doing as x gets infinitely large? Well, we just said it gets infinitely large. And so we have this infinity minus infinity situation, which is not necessarily 0. It may be or it may not be, because infinity is not a number, right? The idea is that these are both approaching infinity at a certain pace. And so it could be that this one is going faster than this one, possibly, in which case the overall y values of the difference will be getting bigger and bigger, and the whole thing will go to infinity. We call that diverging. Or it could be the other way around, where the second one is going to infinity faster. And then you have this difference that's getting larger, negative, and the whole thing goes towards negative infinity. Or they could approach infinity at roughly the same speed, and the difference evens out to 0 or some other constant. So we don't know yet. But this is the general approach that you are going to take when you have a situation like this that's infinity minus infinity. You want to use the conjugate pairs method. And so what I'm going to do is force this to be a fraction by multiplying it by its conjugate pair, which is the same terms but connected by the opposite sign. So it's square root of x squared plus 1 plus x, and I'm going to multiply that over itself. And now, if this is a and this is b, I know that my numerator is going to multiply out to be in the form a squared minus b squared, where a squared is just x squared plus 1, and b squared is just x squared. And then I'll have that over root x squared plus 1 plus x. Okay. Notice that the x squareds cancel each other in the numerator. I'm just left with the limit as x approaches infinity. Of 1 over the square root of x squared plus 1 plus x. Now I do have a fraction, and I can kind of use those rules from before. So divide by the highest power of x in the denominator. What is the highest power of x in the denominator here in the chat? 2. So be careful and look at the overall idea. There is a power of 2, but what's it underneath? It's technically underneath a square root. So what's the square root of x? So technically x to the first power. So even though we do have an x squared, since it's underneath the square root, we have to take the square root of that, and we still get x to the first power, which is what we want to divide everything by. So just numerator and denominator get to dividing by x. Go ahead. So then it would be, if you had x cubed under the square root, then that's the same as x to the 3/2, right? Whoops. So you'd be dividing everything by x to the 3/2 in that case. All right, so we got to do a little trickery. Sorry, I'm planning in my head at the same time because it's clearly not going to be the case that we take the test on Wednesday, but we can't go a week in between either. So I'll talk about what I'm thinking in my head is that I'll give you Wednesday, we can kind of finish this up and do 116, which is real short. And then I think I'm going to open this up as just a take-home test, and it's just going to be due by end of break. So you can do it early and finish it by Friday if you like, or you can take some time and work on the review. But then that gives you sort of Wednesday to ask me questions. I know there's not a lot of test security in that, but there's also not a lot of test security in me trying to stare at you over Zoom taking a test. So I think that's going to be my plan here. All right. So we have 1 over x in the numerator. In the denominator, we have plus, let's see, x over x. We got to sneak that x under that square root. So once again, to sneak the x under the square root, because what I have right now is this, I need to divide by the equivalent, which would be the square root of x squared, right? So underneath the square root, in that radicand, you're going to be dividing by x squared instead of just x, which now gives me the limit as x approaches infinity. So I got 1 over x up here. That x over x just simplifies to 1. Under the square root, I'll have x squared over x squared, which is 1 plus 1 over x squared. And now I'm ready to evaluate. I can do all my terms separately. So what does 1 over x approach as x approaches infinity? That's it. That's going to 0. The 1 will stay as 1. It's a constant. What does 1 over x squared approach? Also 0. This one stays a 1. So now I have 0 over the square root of 1 plus 0 plus 1. That's 0 over 2, which is 0. So again, on like a test, I have to see that algebraic work. But if you can't figure out how to get started, I would do a table and let x get really large. You'll start to see it's getting really close to 0 and see if that can kind of trigger your memory. All right, so I was asked to go back to take a look at a different one. Sorry, in the chat. What was it, this one? Was the question, why does 5 over x approach 0? So 5 is just a constant, right? X is getting infinitely large. So if you think about fractions where the denominator is just getting larger and larger, that fraction is just getting closer and closer to 0. Does that make sense? So if you pop those in your calculator, you're just going to see decimals that get closer and closer to 0 because x is approaching infinity. Anytime you have a numerator that's just a constant, but the denominator just keeps getting larger and larger, overall that fraction will approach 0. Yeah. All right, let's do one more. So we had a limit law that said if we had composite functions, we could take the limit of the inner function and then just evaluate the outer function at that limit. And what that means is that I can look at this as sine of the limit as x approaches infinity of 1 over x. Well, what do you know 1 over x to approach as x approaches infinity? So 0, meaning that inside limit just approaches 0. So this is going to evaluate to whatever sine of 0 is. The sine of 0 is, if you don't remember, got our unit circle. Angle 0 is right here. That's the point 1, 0. Sine is the y-coordinate, so sine of 0 is 0. Good. So this is an example of one of these dampening functions. If you look at it in GeoGebra, this one kind of oscillates way more quickly as you get close to the origin, but then as we move out, it stabilizes and will approach 0 as x approaches infinity.